Good morning children and welcome back to your chemistry class. So today in this S block elements chapter we are going to study about group 2 elements. So group 2 elements, they are also called as alkaline earth metals. And what are those alkaline earth metals? They are, for example, your beryllium, then magnesium, calcium, strontium, then we have barium, radium and all these. So what are they collectively called as? They are termed as alkaline earth metals, right? So today we are going to study about the atomic and physical properties of group 2 elements. So to begin with, let us talk about their electronic configuration. Okay, electronic configuration. So these elements, their general electronic configuration is what? Ns2, right? So for example, magnesium, the atomic number is 12. What is it? 1s2, 2s2, 2p6, 3s2, right? So 6, 4, 10 and 2, 12. So we have Ns2 over here. Similarly, for calcium, it is 20. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So again Ns2. So I hope configuration is clear to you. So the compounds of these elements, they are predominantly ionic in nature. Clear? Now let's talk about the atomic and ionic radii. So the atomic and ionic radii of these alkaline earth metals, they are smaller than those of the alkali metals, right? In the same period due to the increased nuclear charge in these elements. So within the group, the atomic and ionic radii, they increase with increase in the atomic number. That is, down the group, the atomic size and your ionic size increases. Now why do they increase? Because the number of shells are increasing, therefore your atomic size is also increasing. Clear? But if we go across the period, then across the period, the atomic size and ionic size, it keeps on decreasing. Why so? Because the nuclear charge is increasing. So the force of attraction or nuclear pull increases, and thereby the atomic size and ionic radii, they decrease. Clear? The atomic size and ionic radii, they decrease. I hope till here it's clear. Then third point, let's talk about the ionization enthalpies. Now why I'm going little fast? Because though we have already studied about all these physical properties, as well as I have explained everything in detail for group 1 element. So now group 2 element, it becomes very simple and we can go little faster. So what do we know about the ionization enthalpy? The first ionization enthalpy of the alkaline earth metals, they are always higher than those of the alkali metals of the group 1. Why so? Why so? Because the atoms of the alkaline earth metals, they have smaller size and they have higher nuclear charge, right? So if you compare it with the alkali metals. But if we talk about the second ionization enthalpy of alkaline earth metals, they are smaller than those of the alkali metals, right? Now on moving down the group, the ionization enthalpy, as you all know, it always decreases across the period, it always increases. So first ionization enthalpy is higher than alkali metals. Reason? Because their atomic size is smaller and nuclear charge is higher. Correct? But the second ionization energy is smaller than the alkali metals. I hope till here it's clear. Okay. Then we know down the group ionization enthalpy decreases, and across the period ionization enthalpy it increases. Let's come to the fourth point, that is hydration enthalpies. Now, like alkali metals, like alkali metal cations, the hydration enthalpies of alkaline earth metal cations, they decrease on moving down the group. Clear? So over here, if you want to see beryllium ion, it has more hydration energy than your magnesium ion, than your calcium ion, to your strontium ion, and least is that of your barium ion, right? But due to smaller size than that of the corresponding alkali metals, right, metal cations, the group 2 cations, they are more extensively hydrated, and therefore we find compounds like MgCl2.6H2O or even CaCl2.6H2O and so on. So why is it so? Due to smaller size than that of the alkali metal cations. Therefore, they show more hydrated compounds than the alkali metals. Now let's talk about the electropositive character. Electropositive character. So the electropositive character of group 2 element, it always increases from beryllium to radium, right? Why so? Because the atomic number increases. However, an alkaline earth metal is always less electropositive than an alkali metal of the same period. This is what you need to remember. But in the group, what is happening? Because atomic number is increasing, therefore the electropositive character is also increasing. The alkaline earth metal, they act as a strong reducing agent. Why? Because they have Ns2 valence electrons which they can lose, right, in a chemical reaction. For example, beryllium, it is an exception. Beryllium, it is an exception as it has a tendency to form covalent compounds, right? Otherwise, rest all other elements, they are good reducing agents but not as good as we have it in the alkali metals, right? Next, we talk about the density of the alkaline earth metals. The density of these metals, they first decrease from beryllium to calcium, okay, and then increases as the atomic number increases. Clear? So we can see over here beryllium, it has more density than magnesium, than calcium, but over here calcium will be having less than that of strontium, less than and less than radium. Clear? So this point is clear. The alkaline earth metals, they are harder than the alkali metals, always remember, and therefore the density of the alkaline earth metals, it is always higher than that of the alkali metals, right? The hardness is also because of the strong metallic bond between the atoms of the alkali earth metals, right? So I'll write over here the alkaline earth metals, they are harder than alkali metals. Okay, what is the reason? First reason is I should write down over here. Firstly, the density of alkaline earth metal is higher than alkali metals. Okay, and secondly, the hardness is also because of the strong metallic bond between the atoms. Atoms of what? Atoms of the alkaline earth metals. So I hope the density is also very clear to you. Next we move to melting point and the boiling point of the alkaline earth metals. There is no regular trend in the melting and boiling points of the alkaline earth metals. Why? Because these metals, they crystallize in different types of lattices. So you can learn like this. Order of the melting point is somewhat like this. Beryllium has more melting point than magnesium, which is less than calcium. Calcium has more than strontium, and least is that of barium. Okay, and if we want to check the order of the boiling point, then it is somewhat same but slight difference. Like for example, beryllium, then magnesium, once again smaller than calcium. Calcium has more boiling point than strontium, and strontium has less boiling point than barium. So here you will find the difference. Melting point of strontium is more than barium, and boiling point of strontium is less than barium. Clear? So all this is why? Because the different types of lattice that is formed, right? Next we move to the oxidation state of alkaline earth metals. Oxidation state of alkaline earth metals. So these alkaline earth metals, they show an oxidation state of +2 in their compounds, right? So the alkaline earth metals, they have the tendency to get oxidized in the aqueous solutions, but this tendency increases from beryllium to barium, and this is reflected in their oxidation potential. The values could be like, which is in the solid state, gives an ion and loses 2 electrons to form the cation. Okay. Now since the oxidation potential is positive, therefore the process of oxidation is also quite spontaneous. Now let's talk about the coloration or the color of the flame. Okay, so beryllium, it does not impart any color to the flame. Magnesium, I'll write it down over here, beryllium has no color, whereas magnesium, it burns with a dazzling white light. You already know that. Dazzling white light, right? And other metals, they impart different colors. Like for example, calcium, it gives us brick red color, isn't it? Barium, it gives us apple green color. Then we have strontium, it gives us crimson color, crimson red color, right? And radium, it also gives us carmine red color, carmine red color. So strontium, it imparts, if you see, crimson red color. Why? Due to the Bunsen, because when the valence electron, it jumps to the lower energy state from the higher energy state, after excitation, the energy given out, it corresponds to this frequency of giving us the crimson red color. While the energy given out in the case of beryllium does not correspond to any frequency of the visible light, and therefore we do not find any color of beryllium, or we can say that beryllium does not impart any color to the Bunsen flame. I hope all these atomic and physical properties are clear. Before moving to some important compounds, let us also understand the anomalous behavior of beryllium. Okay, so the first point about it is that it exerts high polarizing effect, right? It exerts high polarizing effect on any anion associated to it. Okay, so that beryllium compounds, they have covalent character and they get easily hydrolyzed. Therefore, they show covalent character and easily get hydrolyzed. I hope this point is very clear. Then it also differs due to its small atomic size. It has high electronegativity, and some more differences could be like it does not exhibit coordination number more than 4. It does not exhibit coordination number more than 4, but the other members of this group, they have a coordination number of 6, making use of the d orbitals. Clear? Whereas other members have coordination number of 6, making use of the d orbitals. Clear? And another point about beryllium is that the oxide and hydroxide of beryllium, they are unlike any other elements in the group. They are amphoteric in nature. Clear? The oxide and hydroxides of beryllium are amphoteric in nature, whereas if you talk about any other element, they show basic nature. I hope this point is clear. Now another point, that beryllium, it shows a diagonal relationship with aluminium. So what all properties of beryllium resembles aluminium? So first point, like aluminium, beryllium is not readily attacked by acids because of the formation of the oxide layer over the surface of the metal. Clear? So should I write it down over here? Diagonal relationship with aluminium. So the first point, as I told you, that they readily get attacked by the do not get attacked by the acids, right? Because of the formation of the oxide layer formation. This is one point of similarity, right? The second point of similarity is what? That the chlorides of both these elements, they have bridged chloride structure in the vapor phase. Both the chlorides are soluble in organic solvents and they are strong Lewis acids. Their chlorides, right, they are soluble in organic solvents and act as Lewis acids. Okay, they are Lewis acids. And lastly, they have the tendency to form the complexes, like for example, both of them, they have the tendency to form complex ions. Clear? So these were some of the similarities of beryllium with aluminium. Now we shall study about some important compounds of magnesium and calcium which are there in your syllabus. Let's start with the first compound, that is calcium oxide. This calcium oxide, CaO, it is also called as quicklime, right? So let us first understand the preparation of it. It is manufactured by heating the limestone, that is CaCO3 at 1070 Kelvin, and there it gives us the quicklime CaO plus CO2, and this is done in an open kiln, right? Now what are the properties? So with water, let's see, with water, what are the reactions it is going to show? It absorbs moisture and carbon dioxide on exposure to atmosphere, and right? So CaO plus H2O, it forms CaOH whole twice. It can also combine with carbon dioxide and form calcium carbonate, right? Then with silica, let's see, calcium oxide combines with silica. On heating, it gives calcium silicate. Clear? So now let's talk about some of its uses. It is used in the manufacture of cement and glasses, in the purification of cane juice, in the sugar industries. It is also used for making soda lime. If you remember, what is soda lime? It is the mixture of NaOH plus CaO. So where is this used? In the decarboxylation of the carboxylic acids. Then it is also used for drying gases. It is also used as a flux in the metallurgy. Clear? So this was something about calcium oxide. Next compound that we have is the slaked lime. This is your slaked lime, that is calcium hydroxide, which is also called as your slaked lime. So this is prepared by treating lime with water. CaO plus H2O, we get CaOH whole twice. The evolution of heat in this reaction is called as slaking of lime, right? The paste of calcium hydroxide in water, it is called as milk of lime, right? A clear aqueous solution of this calcium hydroxide is also termed as lime water. What are the uses for this slake lime? It is used in the identification of certain carbonates, turning lime water milky, in the whitewashing, in the manufacture of bleaching powder, and even it is used for softening of the hard water. Clear? All these uses are clear for slake lime. Next compound that we have is calcium carbonate, right? It is prepared by passing carbon dioxide in the slake lime. So CaOH whole twice plus CO2. When we pass carbon dioxide through slake lime, we get calcium carbonate and water is given out. Now, what are the uses of this? It is used for making building materials, right, in the form of a marble. Then it is used for the manufacture of quicklime. The mixture of your calcium carbonate and magnesium carbonate, if you remember, it is used as a flux in the metallurgy of the metals, like for example iron. Then as an antacid it is used for the mild abrasive in the toothpaste. It is also one of the constituents of your chewing gum, and also it is used as a filler in the cosmetics. Okay. The last compound that we have for calcium is your calcium sulfate, which is also called as plaster of Paris. Plaster of Paris, that is CaSO4 dot half H2O, right? Now, how is this obtained? This is obtained by heating gypsum at 393 Kelvin. So, your gypsum is CaSO4 dot 2H2O. So, two molecules of gypsum on heating at 393 Kelvin, they give us plaster of Paris, CaSO4 dot H2O plus 3H2O. So this is your plaster of Paris. You may write here half H2O. Above 393, no water of crystallization is left, right? And calcium sulfate alone is formed. So this is known as dead burnt plaster. Above 393, this CaSO4 will be called as dead burnt plaster. Clear? It has a remarkable property of setting with the water, and it forms a plastic mass which sets into a hard mass within 5 to 15 minutes on when it is mixed with water. Then what are the uses of plaster of Paris? They are used in the building of industry as well as plasters for immobilizing the affected part of the bone fracture or the sprain that has happened. It is also used in the dentistry. Then it is also used for making casts of statues and birds, etc. Right? Now next we come to another important point. What is the biological importance of magnesium and calcium? So an adult body, already contains 25 grams of magnesium and around 1200 grams of calcium, compared to only 5 grams of iron and little part of traces of copper also. So the daily requirement of calcium and magnesium ions in the human body has been estimated to be around 250 to 300 mg. So it is of biological importance. All the enzymes that utilize ATP in the phosphate transfer require magnesium as their cofactor. What are the other biological importances? Like the main pigment for absorption of light in the plant is chlorophyll, which also contains magnesium. Then about 99% of our body, calcium is present in the bones and in the teeth. Then calcium also helps in neuromuscular transition, in the cell membrane integrity, and even in the blood coagulation. So this calcium concentration in plasma, it is regulated at about 100 mg per liter, and this is maintained by calcitonin and parathyroid hormones. So that was all that we had to discuss in this particular chapter of S block elements, and with this we wind up with the chapter as well. Thank you for today.